Hello, today we will be showcasing the development of our greenhouse companion, Lyco Tomi. My name is Esteban Aragon, I'm a mechanical engineer, the team lead, and I was in charge of the fabrication of our robot.
My name is Tal Monet, and I'm a computer engineer. I was in charge of the electrical fabrication and the programming for autonomous navigation.
My name is Kayla Mellendorf. I'm a biosystems engineer, the procurement lead, and I was in charge of project management.
Hello, my name is Roberto Enrique Diaz. I am a biosystems engineer and I was in charge of the pest identification model.
My name is Ramon Partida. I am a software engineer and I was in charge of the mobile application software.
My name is Walter Davenport. I'm a mechanical engineer, and I was responsible for the design and fabrication of the robot.
The engineering design process is an important part of learning to be an engineer. In this poster, and as you'll experience through this video, we face the problem presented to us, we do our research, and with input from our sponsor determine the required verifications that must be achieved to have a success. With these constraints in mind, we follow through during the design process, ensuring we remain within the budget and the scope of the project. The results showcase how we've managed throughout this course and give us valuable experience towards becoming engineers.
Our project, Lyco Tomi, short for Lightweight Yield Crop Optimizer Tomato Interface, aims to reduce manual labor for staff at the Controlled Agriculture Research Greenhouse and eliminate the risk of allergens that arise from the deployment of pollinating bees. The research greenhouse also implements long working hours, inspecting each sticky trap in the greenhouse looking for insects harmful to the plants, which has slowed operations and increased labor costs.
Our initial research for this project started by learning about tomato crops, which can grow up to 13 feet tall. Additionally, we determined that pollination can be achieved through agitating tomato flowers. To determine the best design, our trade studies compared different pollination methods and the mechanisms needed to reach all tomato flowers. The pollination methods we considered were vibrating the stems, stimulating the guide wires, and using fans to agitate the crops. The mechanisms we considered were a scissor lift, a cascade elevator, and a static structure.
Our initial research for the pest identification model focused on understanding the object detection and machine learning, which led us to select the YOLO B5 model due to its fast and accurate performance for real-time computer vision tasks. After establishing the model, we evaluated hardware options and incorporated the OAK-D-like camera based on a sponsor request. Through documentation and existing implementations, we confirmed that YOLO B5 could be successfully deployed with the OAK-D-like camera using the Depth AI framework, allowing for efficient image capture and real-time pest detection.
Our project system requirements were established with input from the sponsor and the scope of the project. These are separated by their respective subsystems: mobilization, vertical, control, and power systems. We'll go over some of the requirements we've established as key to our project design.
System Requirement 1.1. The Tomi system shall autonomously travel through predefined greenhouse rows. As per standard RIA R15, August 1st, 2020, line following robots stop when obstacles interrupt the line. This standard ensures that there are no collisions with people or crops. System Requirement 1.5. The Tomi system shall be able to traverse over obstacles of a maximum of 2 inches in diameter. The greenhouse Tomi will be deployed in has PVC pipes, all under 2 inches in diameter, along its navigation route.
System Requirement 2.1. The Tomi system shall pollinate tomatoes through agitation. Based on the scope of our project, Tomi must be capable of pollinating the tomato crops. Therefore, any significant agitation of the tomato flowers will achieve successful fertilization.
Here's our model design in SOLIDWORKS. This shows the full integrated system, our vertical system, and mobilization system. Additionally, the model showcases the trade study results, the cascade elevator, and fans for crop agitation. Our first critical design element was a vertical lift system. Based on the design, this system was made by welding aluminum U-channels in a nested configuration, while movement was supported by roller bearings. The finished fabrication shows the aluminum cascade elevator equipped with 2 axial DC fans utilized to agitate the tomato flowers.
Fabrication for our second critical design element started when fabrication for our vertical lift system concluded. This entailed incorporating both the fabrication of the rover and the development of the electrical system that would give our robot movement. The mobilization system depicted here is comprised of a steel welded frame with 4 10-inch pneumatic wheels.
The pest identification model was developed by taking images of sticky traps at the research greenhouse. The insects within these images were classified manually through RoboFlow, from which we could build a database for the YOLO B5 to use to identify the pests. This dataset was then exported and inputted into a working Python model that uses the OAK-D-Lite camera to detect these pests.
The electrical system is designed to meet the specific requirements of our critical design elements. One of the key components is the LiDAR, which measures and helps adjust the height of the vertical lift system. This is important for safety to ensure the lift does not overextend, while also providing exact height measurements for the tomato plants. Another critical component is the Raspberry Pi, which processes our control algorithms and reads the camera feeds, allowing the system to successfully navigate the greenhouse and identify pests. Finally, the system is powered by a 12-volt lithium battery and routed through a fuse block to safely protect all of the electrical components.
The software system is designed to have multiple subsystems operating concurrently. The main software contains the computer vision pipeline for pest identification, computer vision pipeline for obstacle detection, SQL database of seen pests, as well as the web server to host the backend for the mobile Android app acting as its user interface. The mobile app is the main interface for the system, allowing the user to start the mission, drive the system manually, and view and receive notifications from the database. The script building all the subsystems was made using Python and various computer vision libraries. The web server is built through Flask, and the mobile app is built for Android through Java and Android Jetpack.
From these videos, we can see the finished results of Lyco Tomi. We can see that it successfully navigates through greenhouse rows, both autonomously and by manual control through the app. The robot's autonomous navigation works by creating a continuous feedback loop between its cameras and its motors. First, the software processes the active camera feed by isolating the specific tape color, red for the straightaways and green for the turns. The code calculates the center of the line and the exact angle to create a steering path for the robot to follow. When the camera loses sight of the tape at the end of the row, the built-in state machine takes over, which automatically switches to the opposite camera and adjusts the vertical lift position to ensure proper pollination.
After building the dataset with the annotated images, we custom-trained a YOLO v5 object detection model. This model is exported to the pest identification computer vision pipeline in the main software. When the user starts the mission, the system is actively searching for pests and records each observed pest into a database. For pests identified as high priority, the software system sends notifications to the user through the mobile app.
Throughout this project, the team has learned many new skills that we will be taking with us into our future endeavors. Soft skills like time management, conflict resolution, and teamwork, as well as hard and technical skills like welding, technical writing, and programming. Overall, the Tomi team has learned a lot about the design process and how time and project management is key to a successful and fulfilling final result. From all of us at Team Tomi, I hope you had as much fun learning about our project as we did making it. Thank you for listening.